Hi, my name is Kelly, and I'm going to talk about nested domains in the WRF modeling system. A nested domain is the case where you use multiple domains that include a coarse resolution domain with a finer resolution domain embedded inside it. And these domains are typically run together, although later I'll talk about an option where they are run simultaneously. The nest receives data driven along its lateral boundaries from its parent. And depending on your settings, the nest may also provide data feedback to the parent. So how do you know if you need a nest? You should start with what it is you're wanting to simulate and determine how large of an area is necessary to fully encompass that phenomenon. Keep in mind that you do need to have some space around the area of interest to serve as a buffer zone. You then should determine the resolution necessary to resolve the event and then the resolution of the input data. If the input data are too coarse by more than a factor of about 5 to 10 times, then you'll need a nest, as you don't want to have too large of a gap between the resolution of each domain, including from the external model. This can cause unnecessary problems at the boundaries. For example, if you're interested in looking at a 3-kilometer domain, but the input data have a resolution of 1 degree, which is about 111 kilometers, the grid ratio would be 37 to 1, which is much too large. And finally, you need to keep in mind computational costs. If you need to cover a fairly large area, you may want to consider only putting the finest resolution over the exact area of interest and using a more coarse resolution domain to surround it to save on computational costs. The finer the resolution, the more computationally expensive it will be. So this is just an example to show the difference in resolution, and the plot here shows land use types over a pretty large domain. If you are interested in a storm hitting the coast of Louisiana, for example, you may want a domain similar to this one, but the resolution is pretty coarse and you're likely not going to be able to resolve the fine details of the storm. If you use this domain, but instead increase the resolution across the entire domain, that would be pretty computationally expensive. So instead, you could add a nest over the area that is most important with higher resolution, as is shown here on the right. And just using this land use example, you can see the difference in what is able to be resolved by increasing the resolution in an area. There are several different types of nesting. The most commonly used is when we run nests together simultaneously. This can be done in two ways. The first type is to use a single input, meaning the input is only for the course parent domain. This input, which are the MET-EM files from the WPS program, are used during the real.exe program, and all fields are interpolated from the model's course grid. However, this is really only recommended if the nest is over completely flat terrain, like the ocean. If it's over land, you will want to ensure that you're including the high-resolution topography input for the nest. And the only real benefit of this method is to save time running the MET-grid program, which usually doesn't take much time to run anyway. The most common method of nesting is to use input from all of your domains. When run like this, each domain contains the full input data, or the MET-EM files, at their resolution. There are also some specialized nesting options. There are two types of moving nest options. You can choose to build WRF for the specified moving nest option by choosing option 2, which is preset moves when you compile. However, this method can be very tedious to set up because in the name list you have to specify every single move. The other type of moving nest is the automatic move option, which you can build by choosing the vortex following nesting option when you compile. This is used for tropical cyclone tracking and follows the area of lowest pressure. Because tropical cyclones move quickly over a large area, if you wanted to run a 3 to 4 day forecast, it would be very expensive to have a domain with the adequate resolution and to include the entire path of the storm. So an automatic moving nest would be the way to go. The final type of nesting is called end-down or nest down. When you compile with a basic nesting option, you should get an executable called enddown.exe, which you'll use for this option. This is similar to multiple input standard nesting, except you will run your domains separately, running the simulation for the parent and then the child. This can be a useful option if, for instance, you've run a long course domain simulation, for example, several years, and then you later decide you want to embed a nest with higher resolution. It can also be useful if you have several nests with increasing resolution, meaning the size of the innermost domain can possibly be much greater than the outer domain. You'll need many more processors for the large sizes, and you can't use a large number of processors on the smaller domains because you'll get an error. I'll refer you to the presentation on computation for details on this. So it may be necessary to use indown to run the domains separately. You can also choose to use one-way or two-way nesting at runtime. This is determined by the nameless parameter called feedback. For two-way nesting, you'll set feedback to 1, which turns it on in the nameless. With two-way nesting, the lateral boundary conditions are fed to the nest from the parent, and the values in the child domain are averaged to the corresponding point in the parent domain. And these values are then used to overwrite the parent value before the model moves forward. For one-way nesting, you'll turn feedback off or set it to 0. Lateral boundary conditions will be fed to the nest from the parent, but the child values will not be fed back to the parent. There are a couple of reasons why you may choose to not use feedback. One reason is if you are using the indown option. Another is if you're interested in output for all resolutions, the parents and the children, maybe, for instance, for synoptic forecasting plus local forecasting. If you had feedback on, it tends to cause strange squares where you can see the child domain in the parent output, so it's not that great. Some variables, such as land and water points, are what we call masked. This is explained in more detail in the WPS Fundamental Capabilities presentation. When using the feedback option, masked variables are assigned by choosing the coincident center point between the child and parent grid cell. Whatever the value is for the center masked point of the child, it's going to feed that value back to the full cell of the parent. So you can see in this 3:1 parent grid ratio, even if 8 out of 9 of the child cells have one value, but the center cell has a different value, only the center value is fed back to the parent. So now I want to talk briefly about what types of nest setups are okay and what is not okay. Both of these above are allowed. You can have nests with one inside the other, as is shown on the left, but you can also have other nests not included in that periscopic pattern, for instance, as is shown for nest number 4 on the right-hand side. What is not okay is to have overlapping child domains. This technically is okay if you have feedback turned off, but it's not good practice and there's really no need to do it. You're not really saving that much computationally by doing this, so you may as well just combine it all into a single child domain like you see on the right. And then if you needed a higher resolution domain somewhere in there, you can always add that as well. Okay, now I'm going to shift to discussing compile and runtime setup for using nesting. During the configure process, unless you plan to use a moving nest option, you'll choose option 1, which is basic nesting. There are several things that need to be modified for nesting in the WPS name list. You'll notice that the settings for each parameter are in column form. Here we have 2 columns which represent domain 1 and domain 2. You'll also notice that not every nameless parameter has a setting for multiple domains. These parameters are not domain dependent and should be left as only a single value. But for the parameters that have multiple settings, you'll need to set these accordingly for the purpose of running with the nest. For the share section, there are only a couple of things we need to worry about. The first, and probably most important, is to set max DOM to the number of domains you intend to run. Here we are running 2 domains, one parent and its child. You must also set the dates for each domain. And you may have noticed that domain 2 has its ending date and time set to the initial time. This is okay as long as you aren't planning to use nudging or SST update options. It will save a small bit of time as there will only be a single time to process for the nest for initial conditions, and the boundary conditions will all come from the parent anyway. Here we have the GeoGrid section of the name list. The first thing you'll need to set is the parent ID, which identifies each domain's parent. Just to show this more clearly, on the right, we are showing a 3-domain example. Parent ID is set to 1 for the outer domain because it has no parent. It is its own parent. Domain 2's parent is domain 1, so we set the column 2 value to 1. and domain 3's parent is domain 2, so we set the column 3 value to 2. And just in case you're interested in using a more complicated setup like this, I want to quickly show you how this would be set. Just as on the previous slide, we set columns 1 and 2 to 1 because domain 1 is their parent. We set column 3 to 2 because domain 2 is domain 3's parent. And then we would have a fourth column for domain 4 here, and its parent is domain 1, so we set the fourth column value to 1. You'll also need to set the parent grid ratio, which determines the ratio of resolution between the child and its parent. Here we have a 3 to 1 ratio. We recommend odd ratios no greater than 7 to 1, but would prefer you use 3 to 1 or 5 to 1 as those are both broadly tested and show good results. It's okay to use an even ratio if you're not using feedback, and it is possible to use an even ratio even if you have feedback turned on, but it can get messy with feedback, and I'll go into that a little bit more on the next slide. iParent start and JParent start should be set to indicate the start location of the bottom left corner of the nest within its parent. Here the starting location is 70 spaces over in the I direction and 67 spaces up in the J direction. As promised, I want to explain the benefit of using odd ratios. When using feedback, calculated values are fed back to the parent domain from the child along the rows and columns which represent the directional velocities like u and v, and at the mass points for all other meteorological data. As I showed previously, these values are averaged and then sent back to the parent at the corresponding location. When you use an odd ratio, this works out nicely, providing an exact center point for the rows, columns, and mass center point. But if you used an even ratio, it would not be as clean and additional averaging would need to take place. The parameters E_WE and E_SN represent the dimensions for each domain in the west to east direction and in the south to north direction. Actually, the E here at the beginning of the name means the ending point. Here, domain 1 has 175 points in the west to east direction and 145 points in the south to north direction, and domain 2 is 181 by 181. A few things to note. All domains should be greater than 100 by 100 in order to have the space needed to resolve phenomena in the time it takes for large-scale systems to move across. In the practice exercises for our tutorials, we use smaller domains, but this is just for the sake of teaching and saving time and computational costs. In any real application, you will need to use larger domains. You should also try to avoid placing boundaries over complex terrain if possible. I know this is not always the case, especially for domains over the Andes, for example, or the Tibetan Plateau. And you should always keep the nest away from the boundaries of the course domain. As for domain size and for spacing between the parent and child, there must be several rows of cells between domains to be used for communication. The default value for this is 4, but can be modified in the name list. But you will want a much larger buffer zone than that. As a rule of thumb, we advise to keep about 1/3 of the course grid surrounding each side of the nest. This doesn't have to be exact, nor does the nest need to be exactly in the middle of the parent, but it's a good rough guideline to use. To set resolution, you'll set dx and dy, but you only need to set this for domain 1. The GeoGrid program calculates the resolution of child domains based on the parent grid ratio. So just a couple of final notes for the WPS name list. There are no domain-specific settings for the UNGRID and METGRID name list records, so nothing will need to be modified there for nesting purposes. And just one more time, as I mentioned earlier, some name list settings don't need multiple settings for each domain. If the default name list does not have values in more than the first column, don't add any or you will get an error. So now we will move on to the namelist.input file settings for running the real and WRF program. Here we have the time controls section. I first want to point out that the default namelist.input file comes set up for 3 domains. However, for this example, we are only using 2 domains. It's okay to keep your extra columns in the name list. Don't waste your time removing them because later we will set a value to tell the model to only run 2 domains and the model will ignore any additional columns. So you'll first need to set all the date and time information for each domain. These values will almost always be the same for all domains you're using, but it is possible to start the nest later. The history interval declares how often history is written out. Here we have history being written every 6 hours for domain 1 and then every hour for domain 2. When the model writes history, it takes a bit more time, so depending on the size and length of your simulation, it may make sense to have the output written less often for the parent domain, which you're most likely not interested in. Frames per out file determines the number of history intervals that will be included in each history file. Because there is often a lot of confusion between these time and frequency variables, I want to take a minute to explain the differences. Interval seconds is the number of seconds between each input file, which are the MET-EM files from WPS. Here we have it set to 10,800, which means the input is available every 3 hours. The time step, which is in the domain section of the namelist.input, is how often the model integrates forward in seconds. We set it to 180 here, so the model updates its calculations every 3 minutes. The history interval is how often the data is written or recorded. Setting it to 60 means that it's written to a file every hour. And then frames per out file is the number of history intervals within each history output file. In this example, we've set it to 1, meaning that you will only have a single history output time in each output file, so you will get a WRF out file every simulation hour. If we had set this to 3, for example, you would have 3 history times or 3 hours in a single WRF out file. If we set it to something large like 1,000, you could store up to 1,000 history times in a single WRF out file. The domain's nameless record is where you will find the max DOM setting, which you will set to indicate how many domains you wish to run, and here we are running 2 domains. Just as for WPS, you'll set the ending west to east point and the ending south to north points to indicate the size of the domains, and this should be identical to the settings in nameless.wps. evert indicates the number of vertical levels you wish to use. Unless you are doing vertical nesting, this should be set to the same value for each domain. And then you'll set dx and dy to mimic the resolution used during WPS. Beginning with WRF version 4.2, you can simply put the value for domain 1 just as in the nameless.wps. However, if you are using a version prior to that, you will need to specify the value for each domain, and it should be based on your parent grid ratio. So for instance, here we have a 3-to-1 ratio. So if we were using an older version, we would have 30 kilometers in the first column and then 10 kilometers in the second column. Also in the domains record, you'll find the settings for grid ID, parent ID, I and J parent start, and parent grid ratio. These should all be set to the same values used in the WPS name list. This is also where you will set feedback to indicate whether you want to use one-way or two-way nesting. And finally, parent time step ratio, which I'll explain on the next slide. The parent time step ratio is similar to parent grid ratio, except instead of a resolution ratio, it's the ratio of time steps for integration. Let's suppose we have a 3-domain nested simulation with a time step of 180. This means the model will integrate forward every 3 minutes. However, the nest must integrate at a fraction of that time, depending on the time step ratio. Here we have set the ratio to be 3-to-1. Typically, the ratio is set the same as the parent grid ratio, but it does not always have to be that way. There are occasions when it may be necessary to set them differently. So the way this works is since we have a parent time step of 180 and a 3-to-1 ratio for each child to parent, the time step for domain 2 will be 60 or 1 minute, and the time step for domain 3 will be every 20 seconds. First, domain 3 integrates forward 3 time steps of 20 seconds each to get to the time step value of domain 2. Then domain 2 catches up by integrating forward a single step of 1 minute. Domains 3 and 2 repeat this 2 more times until they've reached the 3-minute mark, in which it's then time for domain 1 to integrate forward a single 3-minute time step. And then this is repeated until the full simulation time is complete. I just want to say a few things about the physics section of the name list. For each physics option, you should always use the same settings for each domain, with a few exceptions. If you have a nest with a grid distance of only a few kilometers or less, you should turn off the cumulus scheme for that domain, as you won't need cumulus parameterization. This is explained in more detail in the physics presentation. You may also turn off the PBL scheme for any domains with grid resolutions of about 100 meters. There are some physics time steps that should be set as well, and this setting should be the same for every domain. There is no ratio component for these. The radiation time step should be set according to the domain 1 resolution, 1 minute per 1,000 grid spaces. So for a 30-kilometer dx and dy, RADT should be set to 30. As for the boundary layer and cumulus time steps, these are both computationally inexpensive, so there really is no reason not to go ahead and set these to 0, which means to use them every time step. So where should you start? There are several Namelist templates provided in the test EMReal directory. You can also find documentation in the user's guide and on our Namelist best practice web pages. Recall that not all Namelist options are domain dependent. Always start with a default Namelist. If there is only a single column value, do not add additional columns. And if in doubt, you can check the registry files. You can grep for the parameter name and look to see if it has max DOM listed next to it. If so, this means that the model expects a value for each domain. If not, only a single value should be left in the name list. To run WPS for a nested domain, you simply need to set up the namelist.wps file with nest specifications and then run as usual. After running GeoGrid, you should have a geo_em file for each domain, and after running metgrid, you should have met_em files for each domain. Ungrid will not provide any additional files for nesting, as these are only based on the input data and are not domain dependent. To run the real program, you'll set up your namelist.input file for a nest. You'll then need to link in all of your met_em files and then run real. You should still have only a single WRF boundary file, which includes the lateral boundary data at all times, but only for domain 1. And you will have WRF input files for each domain containing the initial conditions. After you run WRF, you'll have WRF out history files for each domain. If you set restart interval to a time less than or equal to the integration time, you'll also have WRF restart files for each domain. The best thing to do is start with what you're interested in resolving. Determine the resolution necessary and what your computational allowances are. If you determine nesting is necessary, design your course domain first, and once that looks good, then design your nest. After that, choose the appropriate nesting feedback option, and then you are ready to run the simulation. That completes the nesting presentation, and thank you for listening.